In computer science and networking, we often talk about how many bytes of storage we have somewhere, or how many bytes or bits of data are going across a particular medium. And to do this effectively, we have to know the standardized sizes. And so we're going to talk about this today. Additionally, we're going to look at some common bases that are used in computer science, networking, and coding in general. So let's get to it. We already know what a bit is, and it's the foundational unit of measurement, really. So a single bit can contain a 0 or a 1 at any given time. A nibble is a collection of 4 bits, and because there are 4 bits, each of which can contain 2 values, we know that that means there are 2 to the 4th power different bit patterns or bit strings. And so that's 16 values that we can get out of a single nibble. A byte is a now standardized size, effectively, that stores 8 bits. It's the same size as 2 nibbles, and because it's got 8 bits of storage, we can take 2 to the 8th to get 256, and that's how many different values we can store in a single byte. Now I say a byte is now standardized, but this has not always been the case, and it's still effectively not the case because there are machines potentially out there running from before the 8-bit byte, or at the very least there is documentation floating around. And so in networking, they take this relatively seriously, and they don't talk about bytes as much as they talk about octets. But they are supposedly, they basically mean the same thing. So a byte, an octet, they're 8 bits. And today, we rarely will encounter a machine where a byte does not contain 8 bits. So forevermore, when we say byte, we mean 8 bits. And if you see 8 bits, you can call it a byte and everything will be fine. The next commonly mentioned size up from a byte is a word. But a word is a little bit confusing as a term because technically a word is the size of the registers of your target architecture. So if you are on a 8-bit machine, a word has 8 bits because the register size is 8 bits. Unless, of course, for a particular language or the documentation for that architecture, they've decided to identify a word as something larger than 8 bits so that the term word has a meaning other than byte. And this is common in older architectures, especially 8-bit architectures. So we would talk about words as being 16 bits. The idea is, more generally, it's the register size. And today, registers more often than not are larger than 8 bits. So if you have a 64-bit system, we typically would say we have a 64-bit word. If we have a 32-bit system, we have a 32-bit word. Typically, right? But this is still based on generalization and assumption. It's always best to look at the documentation for your particular architecture in case they've decided to provide a specific meaning to the term word or for the particular assembler or tool that you are using. Our book, for example, identifies words as being 16 bits. But this is really not always the case, not at all. Now, once we've established what our word size is, on some systems there will be references to things like double words or quad words. And these are just colloquial terms for double the size of a word or 4 times the size of a word. But you have to know what the size of a word is for these to make any sense at all. We need to be familiar with a variety of data prefixes, and these prefixes really refer to the amount of data that we're dealing with. And we're talking about the amount of data, we mean the amount of bytes, the number of bytes. And these are fairly standardized and you can find them all over the place, but nonetheless there is some confusion. So you see here on the left the basic prefixes, kilo, mega, giga, tera, peta. And you've seen or heard these probably in common forms like kilobytes or megabytes or gigabytes, terabytes, for example. When we're talking about data and byte sizes, we are pretty much always talking about things that are orders of magnitude in binary. So, and they relate to exponents that increase by the magnitude of 10. So a kilobyte is 2 to the 10th. A megabyte is 2 to the 20th, a gigabyte is 2 to the 30th, and then 2 to the 40th and 2 to the 50th, and so on. There are several others with names, but I don't list them here. Now when you go up, when you take your exponent up by 10 each time, you can see in the right column of this table here that that really increases the total number of things by 2 to the 10th. So when you go from 2 to the 20th to 2 to the 30th, you've increased the number of things that you have by 2 to the 10th, which is 1024. So a megabyte is 1024 kilobytes, and a gigabyte is 1024 megabytes, and so on. Now their actual decimal values are listed here, but that's not nearly as important as the concept of the order of magnitude that we're talking about, unless you really are looking for the specific number of bytes. In which case, I recommend that you look for the number of bytes and not for something with these prefixes, because the prefixes have some ambiguity. Now I say ambiguity even though they are standardized by international standards organizations, and they have been, at least in their common forms today, since the 90s. However, there are conflicting current and old standards culturally. So it is very common, and I'm in this boat, to talk about kilobytes, megabytes, gigabytes. We see this as the most commonly in commercials or advertisements for hardware, etc. So it's the cultural norm. But since the mid-90s, or the late 90s, I guess I should say, the standard has changed, and you can see it here on these slides, where instead of talking about, say, how many K or how many KB as the abbreviation, we see this little I show up in the middle, and that's a reference to the alternate contemporary prefix kibi. And so instead of kilobytes, megabytes, and gigabytes, the current IEC standards indicate that we should say kibibytes, mebibytes, and gigabytes, etc. Many tools, many platforms, and many publications have faithfully adopted this standard over the last 20 years. However, it does not have cultural dominance, and so we have to be careful. When you see a capital M and a capital B, I would assume if you are talking about data and storage in computers that we are looking at powers of 2 here. And we mean things like megabytes and kilobytes, or mebibytes and kibibytes. But there is a competing set of prefixes with effectively the same names, and these are metric, right? And these metric prefixes are very common in networking. And so we'll talk potentially also about kilobytes of data transferred, or gigabytes of data transferred, or megabits of data transferred. And when we are in the networking world, almost always we are now outside of powers of 2 and talking about powers of 10 instead. And these powers of 10 don't have exponents that go up by 10. These are base 10 with exponents that go up by 3 at a time. All right, so a kilobit is 10 to the 3rd bits, and a megabits are 10 to the 6th bits, and then we go to 10 to the 9th, 10 to the 12th, etc. All right. Now, unfortunately, the abbreviations for these, as we can see here with kilobits or even kilobytes, when we're talking about networking again, we see that those could be K, they could be KB with a capital B, and sometimes we see a less ambiguous K with a lowercase b, and that I think is very helpful, and it's my preferred mechanism. But you really don't know unless you look. Now, we're also starting to see these metric prefixes, which will be a base 10 rather than base 2, used not for talking about how many bytes of storage a particular file has consumed, but when we talk about things like buying hard drives. Very often now when you look at buying a hard drive or some particular storage medium, it will indicate that it is 3 terabytes or something. And then there'll be a little asterisk, which is great because it's clearing some things up. And you look at the asterisk, instead of it telling you that it's 2 to some power number of bytes, it'll tell you that it's 10 to some power number of bytes. So make sure you look at these references so that you can, or to find these pieces of information so that you know exactly what sizes you are talking about. Now, in just as one other example, in the operating system of my preference, I use a Linux operating system for pretty much everything, and I use the Ubuntu distribution of Linux. When I am on the command line terminal and I look at the files in a particular directory and have it list their size in human forms, I typically get these kinds of abbreviations here, the K, the M, the G. No B's, capital or otherwise, no little I's floating around as in the kibbies or mibbies. And so it's a little ambiguous for me. And I have to either read the documentation to figure that out, or I can do simple experiments, like I could make a file that has exactly 1024 bytes in it, and then see what size it's listed as. Will it be listed as a single K, or will it be listed as some other value indicating that the K is relative to a base 10? Now, in computer science and computer programming, we also need a number of different bases to represent our values. They can all represent the same values abstractly, but we communicate those values in different ways. And the two most common are decimal and binary. Decimal, of course, you grew up with and we're very familiar with, and it's one of the reasons it's one of the most common. The second one, binary, which we're just learning, is also common because computers today are fundamentally based on binary numbering systems. The positional numbering systems are binary. Remember that we moved away from decimal-based systems to binary because it helped us increase the performance of computers, reduce their cost, and reduced their size. But we have two additional bases that are very common. One is octal, and octal is base 8, which means that its coefficients go from 0 up to 7, but they don't include 8 and 9 like decimal. And so each digit represents 8 different values. Now in C, we would see something that appears to be a decimal number, but if it starts with a 0, that's the indication to the compiler that this is actually meant to be interpreted as an octal value. So this is not really 527. It's 5 times 8 to the second power plus 2 times 8 to the first power plus 7 times 8 to the 0th power. So we could figure out its decimal equivalent by writing it down in its coefficient base exponent form and doing the rest of the math to convert it to decimal. In Python, we can also start with a 0 to indicate that it is an octal value. But this has lost favor, and since Python 3, we have introduced the notation of a 0 followed by a lowercase o for octal, and then the octal digits. Please note this is not 00 or capital O, little o. This is 0, little o. In Haskell, we use the same notation as Python 3. Pascal, we use the ampersand before octal digits to indicate an octal number. And in the Mini-AT architecture, for its assembly language, we use a 0 followed by a C. Now, I forgot to mention it up here, but for the same architecture, the Mini-AT, its assembly allows for the communication of binary numbers by starting with a 0 and then a lowercase b. Afterwards, we can represent the binary string as a series of 1s and 0s, and to make it visually clearer in terms of the groupings of 1s and 0s that matter to us, we can insert as many underscores as we like. Now, most languages today don't include support for the representation of binary numbers, and so we'll have to do something else in those languages or for those other platforms. The next commonly used base is hexadecimal. Hexadecimal is base 16, and because it's base 16, it must have to represent values between 0 and 15 with each of its coefficients. However, the coefficient starting at 10 already require 2 digits if we were to list the coefficients using decimal type numerals. And so we don't say 10. Instead, when we get past 9, to indicate a 10, we move on to the letters of the alphabet. And so A is used to be the equivalent of 10, B is the equivalent of 11, E is 14, and F is 15. So they just go right on in a row and you can fill in the blanks I've skipped. In C or C++, we indicate hex values by leading the digits with a 0 and a lowercase x, and it's the same in Python. It's also the same for the mini-AT assembler, which is not listed here. In Pascal, however, for those of you who encounter it or have seen it, hexadecimal values are preceded with a $sign prefix. Now, it's obvious why we want to use decimal and why we want to use binary for representing numbers. Decimal because we are human beings and we think in decimal. Binary because the computers we use are digital and they have numbers and data based on binary values. So also, obviously, we want binary. But what do we need octal and hexadecimal for? So octal, first of all, if you take a particular value, 1,592, whatever that value is in the decimal world, if you represent that value with binary, you're going to end up with a long string of zeros and ones. In that case, for the number I gave, I would assume 11, a bit better than that is 11 bits long before you just start adding extra zeros to the front for no real reason. So if we want to represent that same value in octal, it's going to take considerably fewer digits. And the reason is because we can have more coefficients per digit. So we use fewer digits to represent the same values that we would have in binary. Now it's also valuable, octal, because it is trivially converted to binary or from binary to octal. And that's because they share a common base. So in binary, everything is base 2 to some power. In octal, everything is base 8 to some power. But 8 is 2 to the third. And so any power of 8 is also a power of 2 to the third. And that means we can use, because of that exponent 3, that means if we have a digit in octal, it is equivalently represented in binary by 3 bits. From the same perspective, if we have some binary bit string that is 9 bits long, it has 3 groups of 3, and so we can represent it in 3 octal digits. So that's one big reason. So trivial conversion to and from binary, but resulting in strings that are much shorter, so they're easier to type and easier to read or describe to someone else. Now, in early computers that were being operated by individuals, we didn't want to use things like the old sci-fi movies where there's just rows and rows of bulbs blinking, each representing a 0 or 1. It's just confusing, and again, these numbers that are being represented are very, very long. If we could shrink that down into something that's more compact, easier to read, more meaningful, it's good for us. And so we had these things called 7-segment displays. And you understand these from your basic solar-powered calculator, those zeros that are made up of a few vertical bars and 2 horizontal bars, for example. With a 7-segment display, we could easily communicate all the values or all the coefficients in an octal number. And so for 3 bits of data, we could have a single 7-segment display, and it was easy for us to read, as well as to verify input that we were going to provide if we were using some kind of switched entry. Also, computers like the PDP-8 and others from that time period had word sizes that were multiples of 3. For example, there were 12-bit words, 24-bit words, 36-bit words. And because each of these are multiples of 3, the 3 bits that you could break these down into, the 3-bit patterns you could break these down into, were easily represented with octal. In more modern terms, since nobody's really using PDP-8s for stuff today, other than just for the pleasure of doing it, if you are a Unix or Linux user, and so that includes if you're a Unix user, Linux user, or specifically like a Mac user that has a Unix-based or Unix-style kernel, in those systems, file system control is done with something called discretionary access control, in which every file, every directory has associated with it some rights. And those rights are distributed between whoever owns that particular file object, whoever is in the same group as the owner of that object, or I shouldn't say in the same group as the owner, excuse me, but the same group to whom that object is provided. And then you also have controls for everyone else, so not the owner specifically and not the group of the object specifically. And for each of those three categories of individuals who might access the resource, you can identify one of three different things. So read, write, or execute capabilities. So we have three groups that we might want to, or three parties that we might want to expose a resource to. And for each of those three, we have three different rights. So all those threes remind us of 3 bits, which can be represented as octal. So you see here in this example on the slide, the octal string 754, noted as octal because it is led by a 0. So that breaks down into the bit pattern 3 ones for the 7, 101 for the 5, and 100 for the 4. And each cluster of 3 represents the list of entities that I have up here. So the first 3 is for the owner. The second 3 is for the group that the resource is assigned to. And then the last 3 is for everybody who might have access to this computer system at all. And each of those 3 bits in order for each of those 3 entities is going to be the read, write, and execute bits. So when we break down a 754, effectively what we're saying is that the owner has full control of whatever that resource is. People that are in the group that this object is assigned to have read, because that's the leftmost one here, and execute capabilities. So the one means that capability is turned on. And everyone else only has the ability to read that file. So why hexadecimal if octal does all this great stuff for us? Well, similarly to one of the advantages of octal over binary, hexadecimal uses fewer digits than both binary and octal values or numbers for the same value. And like octal, it is trivial to convert between hexadecimal and binary in either direction. But in the case of hexadecimal, since it is base 16, which is 2 to the 4th power, we have the common base of 2, and because it's 2 to the 4th, that means each hexadecimal digit represents 16 different values, which is represented by 4 bits. So a hexadecimal digit is equivalent to 1 nibble's worth of data. Now, in the modern world and for the foreseeable future, our word sizes will not be multiples of 3. They are going to be powers of 2. Right? So we won't see 12 and 24 and 36-bit machines very much now or in the future, but we will see 32-bit, 64-bit, 128-bit, etc. Right? And as long as the power of 2 that these word sizes are, that these register sizes are in machines, as long as that power is greater than 2, then whatever it is, like 64, is definitely divisible by 4. And so that means we can break up any values representation into a series of nibbles, complete nibbles. And that means into the future, it will be extra easy to take any word size value, its actual bit string, and break it up into a series of nibble-sized chunks, 4-bit chunks, and then represent each of those nibbles with a single hexadecimal digit.